Hello and welcome. In this presentation, I will be discussing the modeling of a particle in a box and to find out the behavior of a particle in a confined environment and to understand its wave-particle duality using Python. First thing we're going to discuss is why we need a box. Now, the reason we use a box is because when the environment is not confined, because of the probabilistic nature of particles, it is impossible to predict where the particle will be and how it will move. But when we have it in a confined environment, then we are more easily able to model and predict how it will move and where it will be inside that environment, which will help us make assumptions and understand more about the particle behavior outside of this environment. Now, for this, we're going to need to use this expression, which comes from the Schrödinger equation. Psi gives us the behavior of the particle in this environment. A is the normalization constant, which comes from the integrated Schrödinger equation when there is a 100% possibility of a particle existing in the environment. L is the parameter of our box, or the length of the box, and x and y are the dimensions that the particle is going to be in. So we're going to have 3 dimensions in the environment to look at, and the particle is going to be in the x and y dimensions. To find the probability density of this particle inside this environment, we use the modulus squared function of this formula, which gives us a positive probability density where all of the probability of the particle existing in the environment will be positive. Now, to understand the code that we used to do this is we take a look here. First thing we do is we import 3 packages that will help us in this process. The first package, numpy, is where this will help us extract functions that we need in the formula, like sine, pi, and for other formulas maybe we could use an exponential or something like that. The second line of code helps us gain the ability to plot these wave functions and show what we are trying to model. The third one helps us make this environment in 3 dimensions, so we can have the 2 dimensions that the particle will exist in and the third dimension where we will be looking at this particle behavior. And then we define both L and A after that in the subsequent lines. After that, we define the parameters. We define the dimensions and how the data will move in those dimensions and in how many intervals. So for x and y, we will be going from 0 to L, which is the length of the box, in intervals of, in this case, I've defined it as bat, so 499, which will affect the way the wave looks like, the wave function looks like, and how sharp it is, as we'll see later. And then after that, we will want to give a value for n and define the wave function that we explained earlier, and then make a mesh grid which will help us look at this in a 3-dimensional environment, and then make an array of n so it can show you the wave particle for different quantum numbers, n equals 1, n equals 2, n equals 3, so it goes from 1 to 3. And after that, we make it so we can have both the equations for the probability density and the wave function. And then we input those into our for loops, where the for loop is used to make the code more concise and make it easier to code this. Now, these are the results of that code. We can see here the result from the wave function from the quantum number n equals 1, n equals 2, and n equals 3 from right to left on the top, and the way they look like from a top level perspective at the bottom of underneath each 1. And we can see here how the probability is of them being in that environment. Now this is when we model it using the probability density equation, which gives us the probability density of this particle in this environment, which is why you can see everything is positive and there's no negative values. And from a top-down perspective, they are all the same. Thank you very much for watching. I hope this has been enjoyable in some sense. Any questions you have, you may email me. Thank you very much.